So as I mentioned that the matrices format to transform the coupled system to be a uncoupled system, that e to the at is equals to t, which is the transformative matrices and constructed by the eigenvectors, times e to the dt. This d is the diagonal which construct with all the eigenvalues, t inverse. And this is very important format that tells you how the eigenvalue and the eigenvectors help you transform your system to be uncoupled dynamics. Our original solution that's for the x dot equals to a x. The solution format look like x equals to e to the a t x0, so xt. So this is x0. And using eigenvalue and eigenvector transformat, which will be t times e to the d t inverse x0. So this is very important. This is important. This is important. And this tells us that for the system solution that you can just use eigenvalue and eigenvectors to construct with some initial value conditions. And for the stability of the system, stability of the dynamic system. So the stability of the dynamic system is very important for ordinary differential equations. Think about your ordinary differential equations is the change of your dependent variables as function of time. So as time going to infinity, whether the system is dynamically explode or is dynamically stable, which means converge to zero. So for example, for this system, which is written as a continuous format, that the xt equals e to the a t x0 is t e to the dt t inverse x0, where your d is constructed by the lambda 1, lambda 2, dot to lambda n, where is all the eigenvalues. And e to the dt, so e to the dt will be equals to e to the lambda 1 t, e to the lambda 2 t, dot to e to the lambda n t. And let's assume that all the lambda are real numbers. Okay, are real numbers. So if one of the lambda is positive, that means on that direction with this whole complex on that direction, the eigenvalues, eigenvector directions, it will explode. Well, if this lambda is smaller than zero, then it will converge basically e to the lambda t when the t is going to be infinity, then the e to the lambda t when lambda is negative, it will converge. So for the stability, if lambda is over zero, t going to infinity, then the system will be explode, means unstable. Okay, and if you lambda, some lambda, just one of them, if one of the lambda is over zero at that direction, it's not stable, then the whole dynamic of the system is not stable. But if all lambda is smaller than zero, t going to infinity, so e to the lambda t will be going towards to zero, then it will be stable. Okay, so this is how you decide a dynamic system with continuous function. It will be depends on whether your eigenvalue is positive or negative to decide whether the system is stable or unstable. What if my lambda is a complex system, a complex conjugate? you can write this lambda is equals to alpha plus I beta. So as long as this, if all the alpha I is smaller than 0, when t going to infinity, it will be stable. If the alpha I is one of them, if one of them is greater than 0, t going to infinity, it will be unstable. So you can use eigenvalues to decide whether your system is stable or not. And we will make an example regarding this case.